Okay, the second fundamental physical phenomenon that we need to know about um, that comes into play in most electrophoresis separation techniques is a phenomenon called electroosmosis. Okay, so to understand electroosmosis, I want us to consider the chemical environment inside a silica capillary. So silica capillary is this stuff that GC columns are made of. Um, it turns out that they play a huge role in this electrophoresis phenomenon um, in a technique called capillary electrophoresis, which is what we're going to talk the most about. But actually, this phenomenon of electroosmosis, it happens anywhere you have a surface, a charged surface, as we'll see, um, in an electric field. The fused silica capillary is the simplest example of that, so that's where we're going to start. So let's imagine what this thing looks like. So here's the inside wall. I'm going to try and draw this nice and big because there's a lot to draw here. This is the inside volume of a capillary. This capillary is made of glass, it's made of silica, and we've talked about the surface chemistry of silica before. We talked about it when we talked about bonded phases in HPLC. So silica is this siloxane material, right? So in the bulk of the silica, we have these SiO, SiO, SiO bonds, and dangling out into solution, we have silanols, right? OH. But actually, these silanols, so the pKa for silanol is around 2. That means that when pH is greater than 2, these hydrogens are going to leave, and what we'll actually have at all pH is greater than 2 is this condition, where actually what we have is a high density not of OHs on the wall, but of these oxygen ions, this anionic character to the wall. Okay, so if there was nothing else going on in this capillary, that would be the end of the story, but there is other things going on in this capillary. Suppose the capillary is filled with a buffered solution. So I'll remind you that a buffer is something that we use to keep a nice stable pH, right? It's a mixture of an acid and its conjugate base. But it also is a mixture, it's a salt solution basically. So it's a mixture of anions and cations. So these are in solution like this. Here's the thing, the negative charge on the wall is super dense. There's a lot of these oxygens on the wall. So there's this really strong source of anionic character. These cations are going to want to go to the surface and they're going to want to balance these things out. The problem is they're too big to, I guess I haven't drawn an excellent example here because we've got pretty much a one-to-one pairing there. But the point is that the negative charge on the wall is too dense to get a one-to-one pairing. So these cations feel an attraction to the wall, but they cannot get in there close enough to all the densities of these oxygens to match them one-to-one. So we're going to use the bottom wall here to get kind of a clearer picture. Let's imagine a really high density of negative charge here. There it is. Okay, so lots of negative charge on the wall. We get these cations coming in to try and balance that, but they are too big, and the negative charge is too dense to get a one-to-one pairing. And so that means that after these guys have lined up on the wall like this, there's still some residual negative character, and it's going to attract some more cations that can't get any closer because obviously if they could, they would have filled in here. So they're sort of repelled back into this second layer. And we get two names for this. We call this first layer the stern layer, And we call this second layer the diffuse layer. Okay, stern because they are too strongly held to move, right? They are stern and stuck in place. And diffuse because they're both further away and there's lower negative character out here. So these actually can move a little bit in response to a force that we'll talk about in a second. So together, these make up something called the electronic double layer, the EDL, the electronic double layer. Okay, and we have a terminology. We have a quantitative. Let's just show that this is the electronic double layer. We have a quantitative way to describe the electronic double layer. We basically have a number that we can put on this electronic double layer to compare it to other electronic double layers. So let's do that.